Hello and Assalamu alaikum everyone. My name is Arsalan Farrukh and I teach math and physics. In this video, I will discuss how to perform operations between complex numbers. Like if you have to add two complex numbers, you have to subtract two complex numbers, or you have to multiply or divide two complex numbers, then what would be the easiest possible approach towards that? But for that, you may have to recall that the complex numbers can be written down in three different forms. The rectangular form, in which you have a real part and an imaginary part multiplied by iota. And then there is a polar form, which is also called moduli argument form, in which you write it down as r cos theta plus iota sine theta. And also an exponential form, which is just like a restating of the polar form, where you multiply r with an exponential e power iota theta. Now, these are interconvertible forms. Like if you have a rectangular form, you can convert it into a polar form, or if you have a polar form, you can easily convert it into an exponential form or back to rectangular form. And that's very, very important to be able to do these operations efficiently and effectively. So first of all, you might need to recall that if you have a complex number which is c equals a plus iota b, and you want to write it down into the polar form, so what you do is that you find r by using the formula r equals under root a square plus b. Basically, this is all being put onto an Argand diagram where we have a horizontal real axis and we have a vertical imaginary axis with both plus and minus. And you have any particular complex number in the rectangular form being represented by an ordered pair, which is a and b. So a is your real value and b is your imaginary value. So once you have these real and imaginary values, you can find out the moduli and argument. To find the modulus, you would have to use Pythagoras theorem. That is why r is equal to under root a square plus b square. And to find the argument, you'd have to find the angle from the real axis, and that is why the angle is tan inverse b upon a. You take a positive sign of b and a, and you get the angle, which is called the basic angle. And then you use that basic angle to get the argument. For first quadrant, it will be alpha. For second quadrant, it will be pi minus alpha. Because the range of argument that you have to take, that has to be between minus pi and pi. You can use these formulas to find out the arguments once you will get the basic angle. Let me show you how you do that. Like for example, if you have a complex number z1, which is 1 plus root 3 iota, so you can find out its modulus by using 1 square plus root 3 square, and that's going to simplify as under root of 4 or 2. So you'll find the argument as tan inverse of root 3 upon 1, and tan inverse of root 3 upon 1 is basically 60 degrees or pi by 3 radians. So this angle is going to be pi by 3 radians. So you can write it down as c is equal to 2 cos of pi by 3 plus iota sine pi by 3. And you can also instantly restate it into the exponential form as 2 e power iota pi by 3. Now similarly, if you have a complex number which is under root 3 minus iota, you would find out its modulus. That's coming out to be 2. And when you are finding out the argument, that's 1 over root 3, that comes out to be, this is the basic angle. I've ignored the negative sign because the angle actually lies in the fourth quadrant. So the basic angle comes out to be tan inverse of 1 over root 3. That's 30 degrees or pi by 6 radians. So but your theta, if you would apply the formula, see, you have formulas. For first quadrant, it's directly alpha. For second quadrant, it's pi minus alpha or alpha minus pi. But since we have a real part positive and imaginary part negative, so I know this must be lying in the fourth quadrant. And since it is lying in the fourth quadrant, so the angle theta must be directly minus alpha. So it will be minus pi by 6. And I can rewrite my complex number as r, which is 2 cos of minus pi by 6 plus iota sine of minus pi by 6. And you can also use one more identity, that cos of minus theta is plus cos theta, whereas sine of minus theta is minus sine theta. So this is going to become 2 cos pi by 6 minus iota sine pi by 6. Or you could also write this thing into the exponential form as well, as 2 e power negative pi by 6 iota. So these are the ways you can convert from the rectangular form into the polar form or the exponential form. And similarly, if you have a polar form or even an exponential form which can be instantly restated as the polar form, you can easily, in just one step, you can convert it into the rectangular form, because you just have to type it down in your calculator. What is 2 cos of pi by 3? So 2 cos of pi by 3 would be 1 over 2 plus iota sine pi by 3 would be root 3 over 2. And you can simplify it up or open it up and it becomes 1 plus root 3 iota. So the process of converting polar form into a rectangular form is very straightforward. You just have to just type it down into the calculator and you will be able to get your answer. Let's have a look at some more examples. These are like just some solved solutions. I had root 3 plus iota. I know it's going to be in the first quadrant. I found its modulus. I found its argument, and I can get myself both the polar form and the exponential form. 1 minus iota would be into the fourth quadrant. So I found the modulus, I found the argument by putting a minus sign, and then I can write it down into the polar form. And I can also use that polar form to write it down into the exponential form using the Euler's formula. 4 iota is directly lying on the imaginary axis entirely, and I can directly see that its angle is going to be 90 degrees or pi by 2 radians. So I can write it down as its modulus would be under root of 4 square plus 0 square, and that means it's going to be 4, and I can write it down in the modulus and argument form. Similarly, if I have something as minus 3, that's lying entirely on the imaginary axis, so I will choose my argument to be pi. I don't need to use any formula to get the argument here. I'll get the argument, I know the modulus, and I can easily write down the form. If I have a complex number as minus 2 plus iota, real part being negative and imaginary part being positive, means this is going to be lying in the second quadrant. So I can find the modulus by using the Pythagoras theorem, modulus formula. I can find the basic angle and then identify that in second quadrant the argument is pi minus alpha. So I do pi minus basic angle, I get the argument, and I can write it down into both polar form and the exponential form. Likewise, if I have something written down as minus 1 minus 3 iota, I'll first recognize it to be in the third quadrant so that I can recall the formula alpha minus pi for this. So I'll find the modulus, I'll find the argument, I'll apply the formula alpha minus pi, and then I can instantly write it down into the polar form as well as the exponential form. So guys, this is how we convert the rectangular form into the polar form, which is very useful in situations where we have to multiply or divide two complex numbers. Let's see how. So if, like, let's say if I have been given two complex numbers which are C1 and C2, and I've also already directly converted into their exponential forms. So basically it's the same complex numbers. In one situation it is stated as the rectangular form, and in the other situation it is stated as the polar form, which is basically a one-step thing from the polar form. So if I have to add or subtract any pair of complex numbers, then the rectangular form is the most suitable one for me, because if I'm adding the complex numbers 1 plus 1.73 iota plus 2.12 minus 2.12 iota, then I can just simply add the real parts together and add the imaginary parts together. So when I do 1 plus 2.12, that becomes 3.12, and when I do 1.73 minus 2.12, I will get myself as negative 0.39 iota. So see how simple it is when I have to add two complex numbers in the rectangular form. Or even if I have to subtract, like I have to find z1 minus z2, it's just gonna be 1 plus 1.73 iota minus 2.12 plus 2.12 iota. So I can just simplify it out as negative 1.12 and plus, if I do 1.73 plus 2.12, I will get myself 3.85 iota. I can even multiply a particular complex number by something like, if I have to find z1 plus 2z2, so I can multiply it by 2 and then add on to it. So all of this kind of simplification is going to be very easy with this. Although I can multiply it in this form as well, but that's going to be quite tedious. Like if I have to find z1 times z2, so what I'm gonna have to do is 1 plus 1.73 iota times 2.12 minus 2.12 iota. And then what I'm gonna have to do is that this multiplies by this, I get a real value, then this multiplies by this, I get an imaginary value, then this will be multiplied by this, I'll still get an imaginary value, and finally when I multiply this with this, I will get iota square, that will turn into a -1 and I'll get another real value, and I can simplify that. Similarly, if I would have to do z1 upon z2, I'm going to have to do 1 plus 1.73 iota divided by 2.12 minus 2.12 iota, and in this case, if I have to go on with this simplification, I'm going to have to do the process of rationalization. That's again pretty long. I'm going to have to multiply and divide by the conjugate of the denominator. So 2.12 plus 2.12 iota divided by 2.12 plus 2.12 iota. I can again simplify this by multiplying each term. For denominator, my simplification could be easier because I can directly apply the formula a square minus b square. I'll get a real part in the denominator, but this is going to be a pretty lengthy working. At least this helps you sort of identify that how much of the working that would be. But how swiftly or how easily you can do this kind of multiplication and division in the exponential form, I mean, which directly comes from the polar form. So it's like pretty much the same thing, whether you have a polar form or the exponential form, your process of multiplication and division becomes so easy. So you are doing z1 times z2, you will just simply do 2 e power iota pi by 3 times 3 e power minus iota pi by 4. And just see, it's like just finding out the product. So 2 gets multiplied by 3 becomes 6, and e power iota pi by 3 gets multiplied by e power negative iota pi by 4. So their powers are going to be added. So it's going to be a simplification of pi by 3 minus pi by 4. Or you can just directly write it down as e power iota pi by 12. So this is how simply you can just simply multiply these two complex numbers so easily. Even if you have to divide two complex numbers this way, even if you have to find out z1 divided by z2, so you are going to do 2 e power iota pi by 3 over 3 e power iota pi by 4 with a negative sign. And then again, you will simplify the constant terms together. Here, they can't simplify any further, so the modulus remains to be 2 by 3. And the argument, obviously, since you apply the form of indices, so when it goes up, from minus, it becomes plus. Basically, what you're doing is that if you have to simplify these, you're going to subtract their powers. So it's going to become e power iota pi by 3 plus iota pi by 4. And this becomes 2 by 3 e power iota 7 pi by 12. And that's how you can quickly, in very little working, find out the products and the quotients of the complex number. And this also tells you one more piece of information that can be very useful for you in many situations, which is that if you're finding out the product or quotient, you can say that modulus of z1 z2 is equal to modulus of z1 times modulus of z2. And if you notice, their moduli are being multiplied, but their arguments are being added. They're added with their own signs. That's why, because one was negative, it got subtracted, but actually you added them up. So you can get yourself a formula saying that argument of z1 times z2 is equal to argument of z1 plus argument of z2. So you will use this information to solve a lot of questions. That if two complex numbers are being multiplied, then their moduli are multiplied directly, but their arguments are added. Likewise, if you have two complex numbers being divided, then the modulus of z1 upon z2 would be just directly modulus of z1 divided by modulus of z2. Whereas argument of z1 over z2 is going to be argument of z1 minus argument of z2. As you can see over here, when they were dividing, the exponential powers got subtracted, and when they got subtracted, I got the overall argument. So multiplication means modulus would multiply and arguments would add. And division means moduli would divide and arguments would subtract. So you can directly do your simplification this way. So you can use this concept in simplifying situations like these. You have to multiply these two complex numbers. So what you could do is that you could just simply write them down in the exponential form and simplify. Just keep one thing in mind, that whenever you are doing this simplification, just keep an eye on this argument. If this argument, because of addition of angles, it may exceed the range of pi, or it may be smaller than minus pi, in that case you can always add 2 pi to bring it within the interval, or you can subtract 2 pi as many times as you want. So like if supposedly if you got your answer as e power iota 3 pi by 2 and you know that it exceeds pi, so what you can do is that in just one step, so just subtract 2 pi from it and you will get your answer as e power minus iota pi by 2. So just keep an eye on that one thing. You can also even find out the whole square of it, or power 3 of it, or you can divide the squares of the two complex numbers. You can do all of these kind of simplifications by just simply rewriting them into the exponential form and then performing those steps of multiplication and division that you would do with indices, and you can simplify any set of complex numbers that way. And not just that, although I have mentioned it before, but this exponential form is very, very useful in terms of finding out the square root as well. So whenever you have to find out the square root of any complex number, even if it's given in the rectangular form, just rewrite it into the exponential form and just in one step take a square root and add a plus and a minus, because when you take a square root, you get two possible answers. So you will get your answers instantly, even for square roots. Thank you so much, guys. I hope it was useful for you. Please do subscribe to my channel and do give a thumbs up. If you have any suggestions, please write down in the comment box. Thank you.